Yes, student. Now we learn about how the interrupt has serviced. We understand in the last video about the interrupt and the polling. Now when the interrupt has occurred, how this works, the process, how it will be taken care by the controller, as in hardware interrupt as or the software interrupt. So every interrupt is assigned a fixed memory area inside the processor or the controller. Like in the ROM area, it is defined the interrupt vector address. That is what we call as the interrupt vector table, holds the starting address of the memory area assigned to it, corresponding to every interrupt. So interrupt vector table, it has an address that is, as we told, it is in the ROM location, that is it is given the reset. So interrupt vector table for 8051 is as follows. As we know that reset, it is started in the ROM location, it is 000, that is pin number is 9. It is a flag auto cleared. Next we have the internal interrupt 0, that starting address from 003. So all the interrupt, it is in 8 bytes, so that it is be added with the 3. Interrupt 0, that is external interrupt, as we called as INT 0, and timer interrupt 0, 000B, the address. Next, that external interrupt 1, that start from the 0013, that is INT 1, and the next we have the timer interrupt 1, timer 1 interrupt, that is 001B, and we have the serial communication interrupt, it is start with the address of 0023, that is a programmer clear the flags through the serial communication flags. We should remember the vector address. So each address has a separate program with respective to the application. Let me see how this interrupt has service. I will take the simple program. We can see that the ISR, the program has written to blink the LED 5 times, and later it modifies to blink the 3 times, so that once the interrupt has occurred, that whatever the program status word, that is flags content, is pushed onto the stack. Now I am selecting the register bank 3, like I am making that 11 or RS0 and RS1 I am making as 11, so that the PSW value is 18. I am moving on to that. Next, initialize the counter R0 as 10, that is a 16 the value, the counter is initialized that, and I am making the delay R7 as 02, R6 is 00, R5 is 00. So I decrement the R5, instantly it will be decremented 2 bytes, because DJ and ZD take 2 mission cycle. Similarly R6 and R7. So the R7, it has 2 values, totally it takes the sum of the time duration. So now I complemented the P1.6, the LED value I made it as complemented. Now I make the loop of R0 to whatever 10 it has to be come down, that will be goes on of 10 times, and pop back the PSW and clear the interrupt flag. and return back that RETI. So RETI, it is return interrupt. So while return interrupt, all the flags has to be popped back and program counter has to be stored in the address where it is called from. So this is the service program as written in the ROM area once the interrupt has occurred. So this is a simple program to be understand. So let me see that once the interrupt has encountered, how it will serve. First, when the interrupt has received, the controller stops after executing the current instruction. When the interrupt has encountered, the microcontroller stops execution of the current instruction. It transfers the content of program counter and PSW onto the stack, because the status, it has to be retained the present instructions. And once the interrupt has completed, the ISR program has completed, while coming back to your main program, it has to retrieve back from the stack. Similarly, how your call instruction subroutine program works, the same way it is also works, but only the difference, once there we using the RET instruction, but here we are using IRET, that's all. There we are using the call instruction, here automatically interrupt has encountered by using the call in the interrupt with respective to the hardware or software interrupt. It also stores the current status of the interrupt internally, but not on the stack. After this, it jumps to the memory location specified by the interrupt vector table, where in the ROM it may be a timer or serial communication or a external interrupt. Depending upon that, it jumps to the vector table and takes the address where it is specified in the vector table. After that, the code written on the memory area get executed, and that address, whichever the code you written, that will be executed. This code known as a interrupt service routine, that is what we called as ISR, or also we called as interrupt handler. ISR is a code written by the programmer to handle or service the interrupt. Let's say once I start the counter, I want to check the interrupt flag is set or not. I need to check every time that counter has reached the maximum value. Then once they reach the maximum value, that interrupt flag has occurred, that will be set. Then your programmer has to stop. That stop the programmer has written corresponding vector table and vector address. After that routine executed, that is what we call as a servicing, handle the service, interrupt handling has occurred, then obviously all the content from the stack, whatever we stored, the program counter and the PSW, retrieved back and it come back by using the instruction IRET. Let me have the interrupt structure of 8051. As we know that we have the interrupt, external interrupt 0 and 1, timer interrupt timer 0 and 1, and serial communication interrupt RI and TI. So whenever we are going to be using the interrupt 0 and interrupt 1, corresponding 0, 1, like that will be stored in your interrupt register. Once in the interrupt register, if it is 0 or 1, it gives the priority, which is the highest priority is given. So here in IE register, interrupt enable, once the interrupt has occurred, that interrupt is enabled. So that interrupt checks that priority from the instruction point register, interrupt point register. According to that priority, it takes the highest priority interrupt and serviced. That it is checking the every time that interrupt which is the highest priority and executed, and every time it is checking according to the priority wise what we have mentioned. Probably we know the highest priority is an int 0. So once it is interrupt polling sequence has over until the low priority interrupt is executed. So likewise the interrupt structure, it is defined in our 8051. Let me see that interrupt enable register. So here the interrupt enable means whatever we have the interrupt that will be enabling, like EX0 that is external interrupt 0 and EX1 external interrupt 1. Then we have the enable the timer 0, enable the timer 1, ET0 and ET1. And we have the ES serial communication, enable or disable the serial port interrupt. With respect to that, we have the EA, that is enable or disable the interrupt. When EA is 0, no interrupt will be acknowledged. If EA is equal to 1, interrupt source is individually enabled or disabled by setting or clearing its enable bit. So that bit will be 1, then only your all the interrupt will be enabled or disabled with respect to that bits. This is your interrupt enable register. This is what the first will do that. Once it is enabled with respect to the bits IE register. Next we'll have the interrupt priority register, IP register. This is what the IP register in this. So here in IP register, it's all a 8-bit register. So PX0, PX1 external interrupt. If you made it as a 0 for interrupt 0, taken as a low priority. If that bit is 1, it is taken as an highest priority. Similarly for all the timers and as well as the serial communication one. PT0, priority given to the timer 0, PT2, priority given to the timer 2. Likewise, we can give the priority. If it is 0, it is a lower priority. If it is 1, it is an highest priority. So, as we know that priority bit is equal to 1, it is highest, assigned as an highest priority. So, interrupt 0, PX0 that is timer 0, PT0, PX1, interrupt 1 that is external interrupt 1, INT1, timer 1, PT1, serial port, PS0. This is we have the interrupt priority register. So this, let me see that how we can write the programming in 8051 by using an interrupt. Let me do some timer interrupt programming in microcontroller. We have the timer 1 and timer 0 interrupts are generated by time register bit, that is TF0 and TF1. These are the interrupt flag, timer flag. This timer interrupts programming by C code, it's involving. While programming, we configure the timer mode register and their mode of the operation, and then we need to enable the IE register and corresponding timer bit in it. And then the next part is choose and load the initial value of the timer register low and timer register higher value by using appropriate mode of operation. We have the timer 0 mode, mode 0, mode 1, mode 2 operation, like 13-bit, 8-bit, 16-bit. Likewise, we have the mode operation. All we have the mode 4 operation. After that, we set the timer run bit, start the timer, so that we return the subroutine for a timer and clears the value of timer register at the end of the subroutine. So this is the process we supposed to write to generate a timer. Let me have the program. So this is the program we are using timer 0 for blinking LED using interrupt method. So here I am using the SJBIT, the variable blink LED. I taken as a LED will be connected to the port 2.0. The first bit I am connected. I assigned that. Then I am written the ISR subroutine program, that is interrupt 0 for timer 0. Here what I am supposed to do is the variable blink LED is complemented. If it is 0, it will be complemented to 1, or 1 if it is complemented to 0, that will be making 1010. With the timer value, you are initialized the value as TH0 and TL0 FC66. That much of time it is taken, your LED will be on or off. So this is the program, it is written in the ISR. So here I call this automatically by the enabling the interrupt. Like first I use the timer mode. I'm using the mode 1 for timer 0, that is a 16-bit timer. So that I'm using the TH0 and TL0 for FC66, and then here I enable the timer 0 interrupt ET0, and then I'm making timer has to be start TR0 is equal to 1. This whenever enable, the timer has started. So once your interrupt has occurred, that is TF0, timer flag is 1, then automatically this your ISR routine, whatever you written, that will be executed again. There your LED will be switching on or off, it will be doing it. So this is the subroutine program, that is what we call as ISR program. It is written in the ROM area. Once the IT0, that is enable the timer 0 is done. So this will be continue until your timer flag become 1, TF0 become 1. So this is what we know, that timer flag become 1 until your program will be executed. So here we can see that whenever a timer has started, TF0 and TF1, this timer interrupt programming, it has to be checked by routine wise. That is what polling is happening. Similarly, we'll see that hardware interrupt programming. We know the INT0 and INT1 are the two hardware interrupt, external hardware interrupt. They are connected through the pin 3.2 and 3.3 with the port 2. So it can level triggered or edge triggered. If you go with the level triggered, low signal at pin 3.2 enables the interrupt, while at pin 3.2 high to low transition enables the edge triggered interrupt. So that if you given the level triggered, then it will be or edge triggered or high to low. This is the way we can enable the interrupt externally. Let us see the programmable feature of 8051 microcontroller with respect to external hardware. Enables the equivalent bit of external interrupt, that is we are using the IE register. Just we given enable it, IE is equal to 1, that will be enabled. If it is a level triggering, then write subroutine appropriate to this interrupt, or else enable the bit in timer configuration register corresponding to the edge triggered interrupt. Whenever we hardware interrupt is enabled, we supposed to write the subroutine for level triggered one, or else we can enable the bit in TCON register, that is timer configuration register, corresponding to the HD guard interrupt. Let me see that program. Here what I'm doing here is I configure the interrupt 0, int 0, that is equal to 1. That will be enabled by using your enable external 0, that is ex0 is equal to 1, and as well enable the interrupt, that is EA is equal to 1. So these three register I is supposed to do for external hardware enabling, that is int 0. Whenever it is encounter, so then we supposed to write the ISR for interrupt 0. Here corresponding you want to stop or reset, whatever the subroutine you can write it here, that is routine you can write it here, interrupt service routine. Similarly, we have the serial communication interrupt programming. It is used when there is a need to send or receive a data. So that we have the interrupts like TI, and that is transfer interrupt, as well as receiver interrupt RI. These two flags will check your data has transmitted or receiver. The interrupt service routine must examine these flags for knowing the actual interrupt by the logical OR operation or of RI and TI flags causes the interrupt, and it is clear by the software alone. Consider the steps involved in serial communication interrupt programming are: first, what we are supposed to do is configure the interrupt enable register for enable the serial interrupt. Next, we configure the serial communication SCON register for performing the transferring and receiving operation. Write a subroutine for given interrupt with appropriate function. So this is simple program we written. Let's say send the character E through the serial port with the baud rate of 9600 using serial interrupt. So I'm just defined the timer mode. It is timer 20, that is timer 1, and I fix the baud rate with sending the 9600, that is given the higher timer is FD, and serial SCON register I made it as 50. Then enable the timer and enable the interrupt. So whenever I timer enabled it, TR1, so then in the subroutine always I am checking that whatever the TI, if TI is equal to 1, that is timer, the transmitter interrupt is equal to 1, then the character E has to be sended through the SBUF register. Once it is sended, I need to clear the timer 0, that is TI is equal to 0, else I need to receiver should be 0, that is receiver interrupt should be 0. This is what we written as in ISR routine, just transmitting the character, E character. So this is how we can understand the interrupts with timer or hardware interrupt like INT 0 and INT 1 or serial communication interrupts. Thank you very much. Hopes you are understand about the interrupts.